Welcome to Orbit Observer. Settle in. Let the weight of the day begin to leave your shoulders, one slow breath at a time. Wherever you are right now, in bed with the lamp turned low, or on the couch with the room gone quiet, or somewhere in between waking and sleeping, you don't have to go anywhere tonight. You don't have to do anything. All you have to do is listen. And let me carry you a very long way from here, out past everything familiar, out to a small, soft, silent little world that has been keeping a secret for longer than there have been people to wonder about it. So let's go slowly. There's no hurry. There's never any hurry out here. I want to tell you about a moon. Not our moon, the big bright one you've watched cross the sky your whole life. A different one. A tiny one. One so small and so faint that no one on Earth had ever seen it until the year 2004, because it was simply too little and too dim to notice from all the way over here. It circles the planet Saturn out in the cold gold light of the ringed world, and it is barely 3 kilometers across. That's it. 3 kilometers. If you could somehow set it down on the ground beside a city, it would be about the size of a small town or a single large mountain. An object you could stroll the length of in under an hour, if only there were any ground firm enough to stroll on. And there isn't. But we'll come to that. Its name is Methone. Say it softly to yourself, the way you'd say the name of something you didn't want to wake. Methone. Methone. It was named after one of the daughters of a giant in the old Greek stories, one of 7 sisters, and I love that a rock this quiet and this far away carries the name of a character from a myth. But the name isn't the secret. The secret is what Methone looks like, or rather, what it doesn't look like. Because Methone is smooth. Impossibly, unreasonably, almost unbelievably smooth. It is one of the smoothest solid surfaces that human eyes have ever laid on, anywhere in the entire solar system. And when I tell you why, I think you'll find it's one of the most soothing ideas in all of space. But let's begin where we actually saw it. Let's begin with the one and only time anyone got a proper look. The date was the 20th of May in the year 2012. Out at Saturn, nearly 1.5 billion kilometers from the Sun, a spacecraft was moving through the dark. Its name was Cassini, a machine built by human hands, launched from Earth back in 1997, that had spent 7 long years crossing the emptiness just to arrive at Saturn in 2004, and had been circling the ringed planet patiently ever since, taking photographs, listening, measuring, sending everything it learned back home across the dark, in a whisper of radio that took over an hour to reach us. And on that day in May of 2012, Cassini did something it had never done before and would never do again. It flew close to Methone, very close, about 1,900 kilometers away at its nearest pass. That may not sound close, it's roughly the distance across a good stretch of a continent, but out there, where the moons are separated by tens and hundreds of thousands of kilometers of nothing, 1,900 kilometers is practically leaning your face against the window. It was the first genuinely detailed look anyone had ever gotten at this little world. And, as things have turned out, it is essentially the only one we will have for a very, very long time. So imagine those photographs arriving. Imagine the scientists of the Cassini imaging science team, the very same people who had discovered Methone in the first place, 8 years earlier, sitting in the quiet glow of their screens, waiting for the images to trickle in from across the solar system. They knew Methone was small. They knew roughly where it was and roughly how big. But they did not know what its face would look like. Nobody did. It had never been resolved before, never seen as anything more than a single dim point of light. This was the moment the point of light would finally become a place. And when the picture sharpened into view, here is what they found. They found an egg. A perfectly smooth, gently curved, luminous little egg floating in the black. Not a jagged potato of rock, which is what you'd expect from something this size. Not a lumpy, battered, cratered ball, which is what almost every other small object in the solar system looks like. An egg. A teardrop. A shape so clean and so soft-edged that it looked less like a natural rock and more like something that had been turned on a lathe or polished by hand or shaped from wet clay by careful fingers and then set out to dry. It was smooth the way a river stone is smooth, only more so. It was smooth the way an egg is smooth, and across that entire luminous surface, across the whole of that little glowing world, there was not a single visible crater. Not one. Now I want you to sit with how strange that is. Because it is very, very strange. Everything in space gets hit. That's just the truth of the place. The solar system is not empty, it's full of debris, full of dust and grains, and pebbles, and rocks, and boulders, all of it moving fast, all of it eventually running into something. The moon, you know, the one over your own rooftop, is covered, absolutely covered, in craters, some of them billions of years old, each one the frozen memory of an ancient collision. Mars is cratered. Mercury is cratered. The little moons of Saturn, Methone's own neighbours, are cratered, some of them so heavily that there's barely a smooth patch left anywhere on them. Space keeps a record. Space remembers every blow. When something strikes a solid world, it leaves a scar, and that scar can sit there, unchanged, for the entire age of the solar system, a wound that never heals. That's the normal way of things. That's what we expect. A surface out there is like an old table. The longer it's been sitting, the more scratches and rings and dents it collects. And by reading those marks, you can more or less tell how old it is and how hard a life it's had. And then there's Methone, a surface with no marks at all. A table that looks like it was made this morning. A face without a single line on it. So the very first question, the one that surely went through the mind of every scientist looking at those first images, and the one I suspect is going through yours right now, is simple. How? How can a little world sit out there for billions of years in a solar system full of flying debris right next door to moons that are pockmarked from pole to pole and not have a single scar to show for it? There's a version of this story where the answer is we have no idea, it's a total mystery, scientists are baffled. You'll find that version out there, and I want you to gently set it aside because it isn't quite true. And honestly, it isn't nearly as beautiful as the real answer. The scientists were not baffled for long. What they found was something far more elegant than a mystery. They found an explanation so soft and so quiet that it feels, to me at least, like exactly the kind of thing you'd want to fall asleep thinking about. But first, let's be honest and careful. The way good science always is, because the honesty is part of what makes this so calming. When I say Methone has no craters, what I really mean, what the scientists really mean, is that there are no craters visible in the best images we have. And the best images we have came from that single flyby from 1900 kilometers out through a camera that can only see details down to a certain size. Anything smaller than that, any little dimple or pit finer than the camera could resolve, simply wouldn't show up. So the truly precise statement is not methane has absolutely zero craters guaranteed forever. The truly precise statement is at the finest detail our one good look could reveal there was not a crater to be seen. And I actually find that caveat comforting, not disappointing. Because it means we're not pretending to know more than we do. We looked as closely as we could look, and what we saw was smooth, featureless, seamless, clean, and here is where the story turns, and where I think the real gift of tonight is waiting. The obvious guess, the lazy guess, would be that methane is smooth because nothing ever hit it, that it just got lucky, that in a busy, dangerous solar system, this one little moon somehow dodged every rock for billions of years and stayed pristine by pure chance. But that isn't right. That almost certainly isn't what happened at all. Things did hit methane. Of course they did. It sits in the same crowded neighborhood as all those cratered moons. It's been pelted by the same debris for the same billions of years. Methane was struck and struck and struck again, over and over across the long ages. The reason it's smooth is not that nothing ever touched it. The reason it's smooth is that it cannot hold on to a scar. Say that to yourself again, slowly, because this is the heart of it. Methane is not a surface that was never hit. Methane is a surface that forgets. Every impact that ever landed on it, every collision, every strike, every little violence out of the dark, was absorbed and settled and smoothed away, filled back in almost as fast as it could form, until the wound simply vanished and the face went blank again, as though nothing had ever happened. The scars don't last, they can't last. Something about the very nature of this little world means that it erases its own history gently and continuously, so that no matter how much it has endured, it always presents the same untouched, unmarked, newborn face to the sky. Think about that for a moment. A world that keeps no record of what struck it. A surface where every blow is absorbed and then forgotten by morning. Where the dents of the day, however hard they came, are quietly filled in and smoothed over while no one is watching, so that when the light returns there is nothing left to see but calm, blank, seamless softness. I don't think I need to tell you why that image might feel good to a tired mind at the end of a long day, but I'll let it just sit there for now, softly, and we'll come back to it. Because I want you to understand how this actually works, the real physics of it, the true story, no invention, no fantasy, since knowing how real it is only makes it more soothing, not less. But before we get to how methane erases its scars, I have to tell you what methane is actually made of. Because it is not what you think. It is not a rock. Not really. Not in the way you're picturing. Here is a number, and I want you to hold it gently, because it's one of the most astonishing numbers in this whole story. When scientists worked out methane's shape and size and weight, and calculated how densely packed its material had to be, they arrived at a figure of roughly 1/3 of a gram per cubic centimetre, about 0.3. And to feel what that means, you need a thing to compare it to, so here it is. Water. Ordinary water, the water in your glass by the bed, has a density of 1 gram per cubic centimetre. Ice, frozen water, is a little less, a little under 1, and methane comes in at around 1/3 of that. Roughly 1/3 the density of water ice. Let that land. Methane is less dense than ice, much less. It is so light, so airy, so loosely put together that if you could somehow find an ocean big enough and drop methane into it, the whole moon would bob up and float like a cork, because it is far lighter than the water it would be sitting in. A moon that floats. Think of that. A world you could imagine drifting on a lake. How can a solid object be that light? The answer is that it mostly isn't solid at all. A density that low can only mean one thing, that methone is mostly empty space. It is not a dense ball of packed rock and metal. It is a loose, fluffy, barely held together heap of very fine material with enormous amounts of empty space threaded all through it. Like a snowdrift, like a pile of the softest powder, like a bank of dry, cold flakes that have simply drifted together and settled into a gentle mound. If you could scoop up a handful of methone, if there were any way to do such a thing, it wouldn't feel like a handful of stone. It would feel like a handful of the finest, driest, coldest dust you've ever touched. Particles so fine they'd sift between your fingers and hang in the air and refuse to pack down at all. This little moon, in other words, is barely a solid world. It is closer to a floating drift of powder that gravity has gathered up and loosely persuaded to hold a shape. And once you know that, once you understand that methone is not a rock, but a soft heap of the faintest snow, the smoothness starts to make a beautiful kind of sense. Of course, a pile of powder doesn't keep a crater. Of course, a drift of the finest flakes settles and smooths and fills itself back in. You've seen it yourself, in a much cruder way, in snow, how a footprint in very light, dry, powdery snow will soften at the edges, how loose grains slide and settle, how the sharp shape blurs and rounds, and eventually all but disappears. Methone is that, taken to its absolute, gentlest, most complete extreme, out in the cold and the quiet, over ages and ages of time. And because it is made of so little, because it is so light and so loosely bound, methone barely has any gravity at all. This is the part I find almost dreamlike. On a world like this, gravity is so faint, so nearly nothing, that it can only just hold itself together, and it can only just hold anything to its surface. If you were standing on methone, and let's imagine you could, though we'll see in a moment that you really couldn't stand in any normal sense, you would weigh almost nothing. You would be lighter than a feather is here. And the pull holding you down would be so weak, so gentle, that the escape velocity, the speed you'd need to leave the moon behind forever and float off into space, is only a couple of meters per second. A couple of meters per second. That's slower than a person walks. That is barely a stroll. Do you understand what that means? It means that on methone, a firm little jump, the kind of hop you'd make stepping over a puddle without even thinking about it, would launch you clean off the surface and send you drifting away into the dark, slowly, endlessly, never to come down again. You would rise up off that soft, pale surface without any effort at all, turning gently, watching the little egg-shaped world shrink beneath your feet, the golden light of Saturn hanging huge in the black behind it, and you would simply keep going, up and out, into the silence. You couldn't walk on methone. Not really. The moment you tried to take a step, the moment you pushed off with any force at all, you'd be flying. You'd float. There is nothing there to hold you. And it's not just you. It's everything. Every loose grain on that surface is barely bound to the world it sits on. The tiniest disturbance, the softest nudge, the gentlest settling is enough to send particles drifting and migrating across the surface, sliding downslope in exquisitely slow motion, resettling somewhere new. The whole surface is not fixed and locked the way the ground beneath your bed is fixed and locked. The whole surface is mobile, loose, faintly restless, in the most delicate way imaginable. A skin of powder so lightly held that it flows and shifts and rearranges itself, given the slightest reason. Nothing is nailed down out there. Nothing is permanent. Everything is soft. And now, maybe, you can begin to feel how the whole thing fits together. A world made almost entirely of empty space. A surface of powder finer than you can easily picture. So lightly held it barely counts as attached. Gravity so faint it can hardly keep hold of its own dust. Put all of that together and you have a moon that simply cannot keep a scar, because the very stuff it's made of will not stay still long enough to hold one. Strike it, and the impact throws up a puff of that fine powder, but the powder can't fly away. Not entirely, because even that weak gravity slowly reclaims it, and so it settles back down, drifting, sifting, filling in the hole it just made, until the surface is smooth again and the memory of the blow is gone. The scar heals almost as fast as it forms. The face goes blank once more. And Methone floats on, untouched looking, ageless, serene, having quietly absorbed and forgotten yet another impact that would have left a permanent mark on any ordinary world. That is the real reason there are no craters. Not luck, not emptiness, not some cosmic mystery no one can explain. Just a world so soft, so light, so loosely made of the finest cold powder that it erases everything that happens to it and keeps forever the same smooth, unmarked, newborn face. I told you it was soothing, and we've barely begun. Now, before we go deeper, and we are going to go much deeper, slowly, over the next while, into where all that powder comes from, and how a lump this small managed to pull itself into such a perfect teardrop, and what it looks like sitting right next to a moon covered in one gigantic crater. Before all of that, let me ask you something, because part of the pleasure of drifting out here together is knowing there are others drifting along with you, all around the world, in the dark, listening to the very same quiet voice. Tell me, if you'd like, down in the comments, whenever it suits you, no need to move much. Tell me where in the world you are listening from tonight. What city? What country? What corner of this planet? It's one of my very favorite things, to look later and see all the places the quiet reaches, someone in an apartment in a rainy city, someone in a house at the edge of a field, someone half a world away where it's the middle of the afternoon, all of us gathered around the same little egg-shaped moon out at Saturn. And if you're new here, if this is your first night drifting off with me, you're very welcome, and you might like to subscribe so the next slow journey finds its way to you when you need it. There's no rush to do it now. Your hands can stay exactly where they are. It'll still be there in the morning. Because here's what I'd like to promise you for the rest of tonight. We are going to take this very, very slowly. We're going to circle Methone the way it circles Saturn, patiently, gently, coming back again and again to the same soft ideas from slightly different angles, letting each one settle before we move to the next. There is nothing here that will jolt you. Nothing loud is going to happen. No sudden turn, no shock, no twist that yanks you back awake. This is not that kind of story, and Methone is not that kind of place. It is one of the calmest, quietest, softest objects in the entire solar system, and I intend for us to spend a long, unhurried while there, drifting down into it, layer by gentle layer, until you don't quite know where the moon ends and sleep begins. You are welcome to fall asleep before we get to the end. In fact, I rather hope you do. There's no test. You won't miss anything you need. The moon will keep. The powder will keep settling. I'll keep talking, softly, and if you drift off somewhere in the middle of it all, that's exactly right. That's the whole idea. So let's go back to that number, because I don't think we're finished being amazed by it. A third the density of water. Barely there. When the scientists, this was a team led by a researcher named Thomas, in a study published in the year 2013 in a journal about planetary and space science, so this is real, published, careful work, not a story someone made up. When they measured methone's shape and worked out what it implied, that impossibly low density was the conclusion they kept arriving at. And the reason they could work it out from the shape at all is itself a small marvel. One will unfold slowly in a little while. The way methone is curved, the exact geometry of that egg, is the shape a soft, fluid-like, barely bound body relaxes into, and it simply couldn't hold that shape if it were dense and solid. The smoothness and the lightness are two halves of the same truth. A dense, hard little rock would be lumpy and cratered. Only something this soft and this light could be this smooth. The egg shape and the empty craters are telling us the same thing in two different languages. This is not a rock. This is a drift. And I keep coming back, in my own mind, to what it would actually be like to be there. To float, because you'd have no choice but to float, just above that pale, luminous surface. Below you, a world you could see the whole of at once, small enough to take in with a single slow turn of your head, glowing softly in the reflected gold of Saturn. The surface beneath you smooth as a held breath, seamless, unbroken, with no crater, no ridge, no jagged edge, no hard line anywhere to catch the eye, just the gentlest curve, rolling away from you in every direction, soft as a drift of the finest snow, which is more or less exactly what it is. And so quiet, so completely, perfectly quiet. No wind, because there's no air. No sound, because there's nothing to carry it. No sudden movement anywhere, because everything out there happens in slow motion, over ages, in silence. Just you, drifting, weightless, above a little world of powder that has spent billions of years patiently forgetting everything that ever happened to it. You could reach down, slowly, so slowly, and let your fingers trail just above that surface. And if you disturbed a little of the fine dust, it wouldn't puff up and scatter the way it would here. It would rise in the faintest, laziest cloud, hanging almost motionless in the near non-existent gravity. Each grain drifting on its own unhurried path, taking its own slow time to settle back down, sifting, gently, 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 until at last it came to rest, and the surface was smooth again, and it was as if you had never touched it at all. Everything on Methone happens like that. Nothing is fast. Nothing is sharp. Nothing is permanent. It is a world where even the act of leaving a mark is undone almost as soon as it's made, softly, without any fuss, without any struggle, without anything having to try. And I find myself thinking, as I picture that surface smoothing itself over again and again, of how good it would be if the mind worked a little more like Methone. If the dents of the day, the sharp word, the small failure, the thing you said or didn't say, the worry that struck and left a crater, if all of those could be absorbed and settled and gently filled back in overnight by some soft, patient snowfall, so that by morning the surface was smooth again and blank again and ready again, holding no scar of any of it. That's not quite how minds work, I know. But it's how Methone works. Really and truly, out there in the cold, that little moon is doing exactly that, right now, tonight, as you lie here, quietly erasing its own history, filling in its own wounds, keeping for itself nothing but a smooth and untroubled face. And maybe, just by picturing it clearly enough, by drifting close enough to it, some of that smoothness can settle over you too. So that's the shape of what we've found so far. A moon 3 kilometers across, an egg of powder floating out by Saturn, discovered only in 2004 because it was too faint, to see before. Visited exactly once, on the 20th of May, 2012, by a single spacecraft that swept past at 1,900 kilometers and sent home the only close pictures we'll have for the foreseeable future. And in those pictures, a face without a single visible scar. Not because nothing ever struck it, but because it cannot hold a scar. Because it is made of the softest, lightest, fluffiest material, a third the density of water, mostly empty space, with gravity so faint you'd float away from a gentle hop. Its loose grains forever sliding and settling and smoothing every wound back to blankness. But we haven't yet asked the deeper questions, and there are two of them, and they'll carry us a long way into the quiet. The first is that shape. How does something this tiny, this lumpy should be, this insignificant, pull itself into a shape so perfectly, so mathematically smooth, a teardrop, an egg, the exact figure a soft body relaxes into, when much bigger, much more impressive moons all around it are irregular and battered and rough? What is it about Methone that lets it settle into such gentle geometry? And the second question is the one I find the most wonderful of all. Where does the powder come from? Because if Methone is constantly smoothing itself over, constantly filling its craters back in with fresh, fine grains, then it needs a supply of that fine material, a steady, endless snowfall of it, drifting down onto this little moon over the ages. And a dead, tiny, geologically quiet lump like Methone has no way to make such a thing itself. So where is the snow coming from? What is dusting Methone, night after night, age after age, with the finest powder in the solar system? The answer is going to take us to another moon entirely. A moon with a warm, hidden ocean under its ice, and fountains of frozen spray erupting from cracks near its south pole, throwing a mist of tiny ice grains out into space. The powder that polishes Methone's face was never Methone's at all. It was breathed out by a completely different world, and carried across the dark on an invisible ring, and it's still falling, softly, silently, right now. But that's where we're going next. For now, just stay here a while longer, floating above the smooth pale egg of Methone, in the gold light and the deep quiet, and let the softness of it settle over you. There's nowhere else you need to be. The powder is still sifting down, the surface is still smoothing itself over, and we have all the time in the world. Let us begin with the shape, because the shape is where the deepest strangeness lives, and it is the shape that tells you almost everything you need to know about what Methone actually is. When we imagine a moon, any moon, we tend to picture something roughly spherical, or at least roundish, the way a stone you have tumbled in a river eventually smooths its sharpest corners without ever becoming quite perfect. We think of something solid, something that holds its form the way rock holds its form. Because it is, after all, a rock. A piece of the ancient solar system, battered and irregular, cratered and rough, holding the record of everything that ever struck it in the shape of its own wounds. That is what small bodies in the solar system look like. That is what we have learned to expect from them. But Methone does not look like that. What Cassini's cameras showed in those photographs from May of 2012 was something that looked almost impossible given the context. Not a lumpy, cratered, irregular chunk of ice and stone, not anything you would call rocky or rough or battered. Instead, a smooth, rounded, gently elongated ellipsoid, a shape that if you were searching for the right word, you would probably settle on egg. A pale, serene, almost geometrically pure egg, hanging in the darkness above the rings of Saturn. And the longer you look at it, the more extraordinary it becomes. Because objects the size of Methone, roughly 3.5 to 4 kilometers along their longest axis, approximately the distance from one end of a modest downtown to the other, are simply not supposed to look like this. Not in the natural order of small solar system bodies, not by any of the rules we thought we understood. To understand why, you have to think about what normally happens when things are small. Gravity, which smooths the large planets into spheres and pulls their surfaces into hydrostatic equilibrium. The technical term for the shape a body relaxes into when gravity is strong enough to overwhelm the stiffness of its own material. Gravity becomes essentially irrelevant at the scale of a few kilometers. The moon is large enough that its own weight pulls it into a near sphere, though its solid, rocky interior holds some irregularities. Earth is large enough that its surface forms a near-perfect oblate sphere, flattened slightly at the poles from its own rotation. But a rock the size of a hill, 3 kilometers across, the size of Methone, does not have nearly enough mass, nearly enough gravitational self-attraction to do anything like that. Its own gravity is so faint, so negligible compared to the tensile strength of the ice or stone it is made of, that it simply sits in whatever shape it happens to have, preserving the record of every collision that has ever modified it, angular and irregular and scarred and real. Go and look at the photographs of Phobos, the inner moon of Mars. Phobos is perhaps 27 kilometers across, far larger than Methone, and it looks like a battered potato, pocked with craters, ridged with grooves, its surface a comprehensive record of billions of years of impacts. Go and look at Hyperion, one of the stranger moons of Saturn itself. A body roughly 250 kilometers across, and it resembles a battered sponge, an almost comically irregular lump whose surface is so heavily cratered and so unevenly excavated that it does not even rotate in a predictable way. It tumbles. It has no stable orientation. It is, in the truest sense, a chaotic object. And these are moons that are far, far larger than Methone. Bodies with far more gravity, bodies that have had far more chance to pull themselves toward some semblance of order. By every reasonable expectation, Methone should be more irregular than either of them, not less. And yet it is smooth. And yet it is, as best the scientists who analyzed the Cassini images could determine, very close to what they call a triaxial equilibrium ellipsoid. That phrase is worth pausing over, because it is the key to understanding what is happening here. A triaxial ellipsoid is simply an ellipsoid, an egg shape, a stretched sphere that has 3 different measurements along its 3 perpendicular axes. Methone is approximately 3.9 kilometers along its longest axis, 2.6 kilometers along the middle axis, and 2.4 kilometers along its shortest. Those are 3 different numbers, which is to say it is not perfectly spherical, not a simple sphere, but a stretched and gently flattened egg. And the equilibrium part, that is the astonishing part. An equilibrium shape is the shape a body takes when the forces acting on it are balanced. When gravity, rotation, and tidal forces, the stretching pull of a nearby massive planet, have all had time to act on a sufficiently fluid, sufficiently yielding body, and the body has had time to respond to all of them, to flow gently into the configuration that minimizes the energy held in its shape, the configuration where every surface is at rest. The shape water in a slowly rotating container would take. The shape of a raindrop in free fall, governed purely by surface tension and gravity, and nothing else. The equilibrium shape is what you get when a body behaves like a liquid. And this is what the researchers who published their findings in the journal Planetary and Space Science in 2013, a study led by P.C. Thomas and colleagues, concluded about methone. That its shape, its smooth teardrop shape, is consistent with a triaxial equilibrium ellipsoid, oriented just as tidal theory predicts, with its long axis pointing toward Saturn, the way a water droplet held in the tidal field of a massive body would orient itself, long end toward the planet. Because Saturn's gravity is pulling slightly harder on the near side of Methone than on the far side, and over time, over the vast unhurried time of the outer solar system, that differential has been able to shape the body. The long axis points at Saturn. The shape is as close to what physics would predict as anything this small has any right to be. And the only way this is possible, the only way a body so small, with gravity so feeble, can relax into a shape that normally requires something to behave like a fluid, is if it actually does behave like a fluid. Or something very close to one. Think of it this way. Imagine you have a bucket of very dry sand, very fine sand, the kind you find at the back of a beach where the wind has sifted and sorted it for 1,000 years. You can pour that sand. You can let it flow. You can press your hand into it and pull it out, and the sand will slowly slump back, fill in the hole, soften the impression you left. It has no real tensile strength. It cannot hold a shape that gravity does not allow. If you pile it too steeply, it slides. If you gouge a channel into it, it fills back in. The sand behaves in a practical sense like a very slow, very granular fluid, and given enough time, a pile of that sand will always settle into the shape that gravity demands of it. A broad, gentle, low-angled mound, the angle of repose, the shape of minimum energy. Methone, the scientists believe, is something like that. Not sand, exactly, it is cold ice, and we will come to what kind of ice and how cold in a moment, but the same essential character. A body whose interior is not a solid, locked, rigid piece of material, the way a granite boulder is solid and locked and rigid, but a loosely packed, loosely gravitationally bound aggregate of countless tiny particles, a body that can slowly, over geological time, rearrange itself, flow at its own microscopic scale, yield to the forces acting on it. A rubble pile, an aggregate. A body held together not by the chemical bonds of solid rock or solid ice, but by the gentle, mutual gravitational attraction of billions of tiny grains, each one holding all the others in a barely there embrace, a grip so light that the whole structure can slowly deform and settle and shift. The word scientists use is rubble pile, and it is a word that has come up with increasing frequency as spacecraft have visited smaller bodies throughout the solar system. The asteroid Bennu, visited by NASA's OSIRIS-RX mission, is a rubble pile. Its surface is covered in loose, unconsolidated material, and when the spacecraft's sampling arm touched down to collect a sample in 2020, it did not touch rock. It sank. It plunged into the surface, as though the surface were a fluid, as though Bennu's exterior were not a hard shell at all, but a slow, granular sea, barely held together by its own negligible gravity. The Japanese asteroid Ryugu, visited by the Hayabusa 2 mission, is similarly loose and porous and aggregate in nature, a body that holds the memory of countless collisions, not in craters chiseled into hard rock, but in the slow mixing and settling of a granular interior. Methone is, as best the science suggests, an extreme version of that same thing. An object so loosely bound, so porous, so granular in its fundamental nature that its density, the density calculated from the combination of its size and its estimated mass, derived from the way its presence affects nearby particles, comes out at something in the vicinity of 0.31 grams per cubic centimetre, just over 0.3 of a gram per cubic centimetre. That number wants some comparison to make sense of it. Water, the familiar everyday standard, has a density of 1 gram per cubic centimetre. Pure water ice, the kind you have in your freezer, is somewhat less dense than liquid water, around 0.92 grams per cubic centimetre, which is why ice floats. Methone's estimated density is only about a third that of water ice. It is less dense, far less dense, than the ice it is almost certainly partly made of, and the only way to account for that is porosity. Empty space threaded throughout the interior, air gaps between grains, a structure that is mostly nothing, held together by almost nothing gravity into a form that barely deserves to be called solid. If you could hold a block of methone's average material in your hand, which, at minus 190 degrees Celsius, you could not, it would feel like holding something lighter than dry snow, lighter than styrofoam, a substance that is more gap than grain, more space than matter, a sort of three-dimensional lace of tiny ice particles touching one another at their edges and holding one another up with the faintest imaginable gravitational attraction. It would crumble at a touch. It would drift away in a breath. It barely counts as a solid at all. And this looseness, this near fluidity of the interior, is precisely what allows methone to wear its smooth shape. A body this loose can flow, not like water flows, not in seconds or minutes, but the way ice sheets flow, the way glaciers creep downhill over centuries, except that the relevant timescale here is millions of years, and the slope being responded to is not a mountain, but the long, gentle tidal gradient of Saturn's gravity. Over time, the loose aggregate that is methone has simply arranged itself into the configuration that those forces demand. The shape of least resistance, the equilibrium shape, the egg. And the same looseness, the same near-fluid character, is what makes the mantle, the outer layer, the coating, behave the way it does. Because here is the other thing the scientists believe about methone, the thing that explains the craters, or rather, explains their absence. When something strikes methone, and things have struck it, in the 4.5 billion years the solar system has been conducting its slow, patient experiment in orbital mechanics, the impact does not produce a clean, sharp crater the way an impact on the Moon produces a crater, the way an impact on Mars produced the Herschel crater, a bowl so enormous and so hard-edged that it looks carved. On a rigid, solid, rocky body, an impact excavates material and throws it outward and leaves a hole that the surrounding rock is stiff enough to preserve for hundreds of millions of years, a scar in stone that holds its shape against gravity because the rock itself holds its shape. On methone, the leading explanation holds. That is simply not what happens. The material is too fine, too loose, too low in internal friction, too close to the behavior of a fluid. The impact makes a depression. And then the depression fills in. The surrounding material, which has almost no internal strength holding it rigid, slumps toward the low point, flowing along the slope the way dry sand flows toward the center of a funnel, the way dust settles to the bottom of a jar. And it keeps flowing and keeps settling, and over time, perhaps quickly in astronomical terms, perhaps within tens of thousands of years, perhaps faster, the depression is gone, smoothed over. The surface has healed itself, not through any active process, not through heat or volcanism or chemistry, but simply through the passive, patient, mechanical behavior of an extremely fine, extremely loose, granular medium yielding to its own negligible gravity. The crater does not survive, not because it was never made, but because the material cannot hold the memory of it. This process has a name in planetary science: relaxation. The same word used in other contexts, in other disciplines, but here meaning the tendency of a soft or granular or viscous material to flow toward gravitational equilibrium, to erase whatever irregularities were imposed on it by outside forces and return to the low-energy shape its structure prefers. Ice does this over long timescales. Even when it is solid, the deep ice sheets of Antarctica and Greenland flow and deform over centuries under their own weight. Methone's material does it far more readily, because the grains are so fine and so loosely coupled that the effective viscosity, the resistance to flow, is almost nothing at all. And there is something else. Something that makes the relaxation even more efficient, even more complete, than the looseness of the interior alone would account for. Methone is not relying solely on its own material to smooth itself. It is being continuously, steadily, gently dusted from outside. The moon sits embedded in Saturn's E-ring. That is the crucial geographical fact, the piece of context without which the full picture of Methone cannot be assembled. The E-ring is one of the broader, more diffuse structures in the Saturn ring system, and it is a very different thing from the bright, tight, famously spectacular rings you see in photographs. The A-ring, the B-ring, the dense icy bands that catch the sunlight and throw it back in great arcs of silver and gold. The E-ring is far subtler than those. It extends from roughly the orbit of Mimas out to roughly the orbit of Titan, a vast, gossamer, nearly invisible veil of very small particles spread over an enormous volume of space, so dilute that if you were floating in the middle of it, you would almost certainly not be able to see it with your naked eye. You would be surrounded by particles, thousands of them passing through a cubic meter of space around you every second, and you would not know it. They are too small, too sparse, too faint. Submicron particles, particles smaller than a single wavelength of visible light. The kind of particle that makes smoke look coarse by comparison. The kind of particle that floats rather than falls, that drifts and disperses and catches light only when you have millions of them together and catch them at the right angle against the dark of space. But they are there, constantly drifting, constantly settling. And Methone is inside that ring, moving through it, sweeping up those particles as it goes. Not violently, nothing about Methone is violent, but quietly, over time, accumulating a slow, steady rainfall of tiny ice grains onto its already loose surface, building up the mantle that covers it, adding layer after infinitely thin layer of infalling powder to the exterior of this already porous, already soft world. The grains are described in the scientific literature as submicron to a few microns in size. A micron is a millionth of a meter. A human hair is perhaps 70 to 80 microns across. So the particles coating Methone are a fraction the width of a human hair, smaller than the finest talcum powder, smaller than the particles in cigarette smoke, smaller than many bacteria. At that scale, particles do not behave the way a grain of sand or a grain of table salt behaves. They do not settle and lock into place. They are so light, so small, so dominated by surface forces relative to their negligible mass, that they behave in some ways more like a gas than like a solid. They drift, they coat, they slip between other particles and fill the spaces between them. They are, in the most literal physical sense, among the finest natural dusts that the solar system produces. And what happens to powder that fine, powder at -190 degrees Celsius in the near vacuum of the outer Saturn system? It stays dry. It stays powder. On Earth, powder at very cold temperatures can behave very differently depending on what the powder is made of and what pressure surrounds it. Ice, at the temperatures and pressures of Earth's surface, melts and refreezes and compacts and crystallizes in complicated ways, driven by the warmth of the sun and the weight of the atmosphere and the chemistry of dissolved air. Snow compacts into fern compacts into glacial ice flows and grinds and transforms over centuries, but take that same water ice and put it at -190 degrees Celsius, the approximate temperature of Methone's environment, deep in the shadow of Saturn, far from the inner solar system's warmth, and things change. The ice is far below its melting point. There is no warmth to drive phase transitions. There is no atmosphere pressing down on it. The particles are not going to compact and weld themselves together. They are not going to form solid ice through pressure, sintering the way snow becomes glacier ice. They simply pile up, loosely, the finest particles resting on the finest particles, in a structure that is more air than ice. A structure that would crumble and disperse with the faintest touch. Cold, dry powder. That is what Methone is coated in. Cold, dry, fine, stable powder. The kind that just keeps accumulating, the kind that fills in any depression almost before the depression is fully formed. The kind that gives Methone its impossible smoothness and its improbable shape and its quality. The quality that, if you could hold the whole concept of it in your mind, late at night, in the dark, with the day settling behind you, of being a surface that keeps no record of anything that ever touched it. There is something almost meditative about the physics of it. The grains fall. They find the low places. They fill the low places. They distribute themselves evenly, smoothly, over the curved surface of this little moon, drawn by its almost nothing gravity, guided by its tidal orientation towards Saturn, until the whole exterior is covered in the same soft, even undifferentiated layer of dust. And, if something strikes, if a micrometeorite, moving fast through the outer solar system, hits Methone and excavates a small hollow in that mantle, the surrounding powder does not hold the walls of the crater up. It relaxes, it flows, it fills, and more powder is falling from the E-ring, always falling, adding to the mantle, replacing what was disturbed, smoothing over the disturbance until no trace of it remains. The surface is reset, continuously, endlessly, patiently reset. It is not that Methone has been lucky, it is not that nothing has struck it, it is that the record of what struck it cannot be held. The powder is too fine, the gravity too weak, the infalling supply too constant, the material too willing to flow. Methone is not scarless because it has been protected, it is scarless because it cannot remember. And the more you sit with that idea, the idea of a world that cannot hold its scars, a surface that every impact smooths over by morning, an exterior that keeps no record of the 4.5 billion years of collisions it has lived through, the more it begins to feel like something more than just a description of a small icy moon in the outer solar system. But we are staying with the physics for now. Staying with the powder and the cold and the ring and the shape, and letting the meaning settle in slowly, the way the powder itself settles. Because the story of where the powder comes from is itself extraordinary. And we will get to it in a moment. The pipeline from the source to Methone's surface is one of the most quietly remarkable things the Cassini mission uncovered, a chain of connections stretching from the deep interior of a completely different moon all the way to the smooth outer skin of this tiny egg. And before we follow that chain, before we travel to the source, the other moon, the one with the warm hidden ocean and the geysers of ice, there is one more thing to say about what methone actually is, about what it means for a world to be made this way. We have said that it is a rubble pile, a gravitationally bound aggregate. We have said that its density is roughly a third that of water ice, and that this implies the interior is mostly empty space, mostly gaps between loosely coupled grains. We have said that the surface is covered in a mantle of fine particles that flows and fills and relaxes. All of this is true, and all of it is consistent with one another, and together they paint a picture of a body that is, in some fundamental sense, not quite a solid object in the way we normally use that word. Not a rock, not a chunk of ice, not anything with the structural integrity of the things we encounter every day. Think about what it would mean to try to stand on it. Methone's gravity at its surface, the faint pull that tiny mass exerts on anything touching its surface, is estimated to be on the order of 1 millimeter or 2 per second squared. For comparison, Earth's surface gravity is about 9.8 meters per second squared. Methone's gravity is roughly 5,000 times weaker than Earth's. On Earth, if you drop something, it falls at a rate you can see, a rate your body is calibrated for. On Methone, the same object would fall so slowly you might wonder if it was falling at all. It would take more than a minute for a dropped stone to fall the height of a person. And the escape velocity, the speed you would need to reach to leave the surface entirely, to pull yourself free of Methone's gravitational grip forever, is on the order of a few meters per second. Roughly walking speed. Less than the speed of a gentle throw. A person standing on Methone, if the surface could support a person, which it almost certainly could not, given that it is a mantle of loose powder floating on a loosely coupled aggregate, so that the first step would likely simply sink without limit into the dust, would need to move with extraordinary care. A firm jump, the kind you might do reaching for something on a high shelf, would launch you off the surface entirely. You would not come down again for a very long time, if at all. You would leave Methone behind at jogging speed, drifting out into the E-ring, surrounded by particles finer than anything in your experience, floating away from the pale, smooth egg in the deep silence, and Methone's gravity would tug at you, gently, but not quite enough to bring you back. And if you pressed your hand into the surface, into that cold, fine, almost weightless powder, it would yield. It would accept the impression. And then, slowly, very slowly, at the speed of geological processes run at near zero gravity, the powder around your handprint would begin to flow. The walls of the impression would slump. The fine grains would drift in from the edges, filling the spaces, smoothing the sharp lines of your fingers and your palm, until the surface was flat again. Until the record of your touch was gone. It would probably take a long time. But the outcome would be the same. The surface of Methone does not hold records. And above it all, above the smooth, pale surface and the almost nothing gravity and the cold, dry powder drifting in from the invisible E-ring, Saturn itself hangs, enormous and golden, and close, roughly 194,000 kilometers away, which in the scale of the solar system is essentially next door, Saturn fills the sky with its rings and its storms and its bands of amber and cream, and its tidal pull stretches Methone gently along the line between them, pulling the long axis of the egg toward the planet, keeping it oriented, keeping it aligned. The way a compass needle aligns with a magnetic field. Methone always shows the same face to Saturn. The long axis always points at the planet. The tidal lock is gentle but absolute. And somewhere in that gold light, in the cold and the quiet and the endless soft rain of particles from the ring, this small, improbable world keeps doing what it has been doing for billions of years, smoothing itself, filling itself in, presenting to whatever is watching the same unmarked, seamless, impossible face. We will not stay here much longer, floating above the surface. The story needs to move outward now, along the chain of connections that brings the powder here in the first place, and that means travelling to the source, to the other moon, the one that breathes ice into the space around Saturn and keeps the E-ring stocked and Methone perpetually coated. That moon is not quiet the way Methone is quiet. It is, in its own way, one of the most astonishing places in the solar system, for reasons that have nothing to do with smoothness and everything to do with heat and water and the question of what might be alive somewhere other than Earth. But its connection to Methone is through the ring, through the powder, through the chain of events that begins with fractures in the ice of a distant South Pole and ends, many kilometers later, with a grain of ice the size of a bacterium settling softly into the surface of this smooth, seamless, record-keeping nothing little moon. That chain is where we are going. But slowly. There is no hurry here. The powder is still falling. The mantle is still settling. And in the cold, golden quiet of the outer Saturn system, the shape of Methone holds, as it has always held, as patient and as smooth and as undisturbed as something that has forgotten everything and kept nothing, a surface that breathes in the dark without making a mark. The journey outward from Methone begins not with a sudden movement, but with a slow realization. The kind that comes when you have been staring at one quiet thing for a long time and you start to notice the air around it, the invisible structure it is embedded in, the threads that connect it to everything else without touching it directly. Methone sits in space the way a pearl sits in a setting, and to understand the pearl you eventually have to understand the setting. The way it holds the thing, the source of the material that gave it its particular luster. And so we move, not quickly, not all at once, but outward, along the invisible river of ice that flows through this part of the Saturn system and deposits its finest grains on the surface of the smoothest world we have ever found. The river has a source. Every river does. It lies roughly 238,000 kilometers from where Methone orbits, which, in the scale of the Saturn system, is not very far at all, a short distance by planetary standards, a neighborhood away. The source is a moon called Enceladus, and Enceladus is, in almost every way, the opposite of what Methone appears to be. Where Methone is small and still and silent and smooth in a way that suggests perfect repose, Enceladus is active. It is alive with process, alive with heat, alive with something happening beneath its own surface that has no parallel anywhere else we have looked in the outer solar system. It is a moon in the grip of forces it cannot contain. And the evidence of those forces sprays outward into space in continuous, quiet, extraordinary plumes of water ice and vapour that have been doing exactly this, as far as anyone can tell, for a very long time. Cassini discovered the Enceladus plumes in 2005. That is the year that changed everything scientists thought they understood about where life might be possible in the solar system, and it is also, though less obviously, the year that gave us the first real key to understanding methone. The two facts are connected by the ring, by the powder, by the long, slow, invisible chain of ice that begins at the south pole of Enceladus and ends in the surface mantle of a 3-kilometer egg of a moon orbiting quietly nearby. The discovery happened because Cassini flew close to Enceladus, close enough to measure things no one had expected to measure. The scientists watching the data come in noticed, among other things, that the space around Enceladus's south pole was different from the space around its north pole, different in temperature, different in the particles drifting through it, different in a way that could only be explained by something happening at the surface. And when the images resolved clearly enough, there they were, fractures in the ice, long and roughly parallel, cutting across the south pole of Enceladus in a pattern that was immediately, memorably nicknamed the Tiger Stripes. 4 of them, roughly 130 kilometers long each, evenly spaced, cutting through the icy crust at the South Pole like claw marks drawn by something immense and deliberate, which of course nothing deliberate had made them. They were the surface expression of heat and pressure building from below, of an interior that was warmer than it should have been, of something working. From those tiger stripe fractures, Enceladus breathes. That is the word that comes closest to what it does. It does not erupt, exactly, not the way a volcano erupts with sudden violence. It breathes, slowly, continuously, persistently, exhaling a mixture of water vapor and tiny ice grains from the fractures at its south pole, sending them up into the cold space, above and away, outward into orbit, where they spread and dilute and spread further until they fill an enormous, diffuse, barely visible ring around Saturn called the E-ring. Cassini measured the composition of those plumes. Water ice, water vapor, traces of other things, but mostly water crystallized into particles of extraordinary smallness, rising from the south pole of a moon 100 miles wide, in a continuous fine mist that is visible, in the right light, as a faint backlit shimmer against the darkness. The tiger stripes are not just surface features. They are windows. They are the places where the pressure and heat of Enceladus's interior find their way out, and what that interior contains, what the heat and the composition of the plumes together imply, is something that took scientists years to fully accept, because it is so extraordinary that it does not feel like it should be true out here, this far from the sun, in this cold and quiet corner of the solar system. Enceladus almost certainly has a global ocean of liquid water beneath its icy crust. Not a pocket of water, not a small localized melt. A global ocean, warmed by tidal forces, kept liquid by the same gravitational kneading that keeps methone in its gentle resonance wobble. The same mechanical process working at a different scale and to a different effect in Enceladus, producing actual liquid water beneath kilometers of ice, water that has been there long enough and warm enough and chemically complex enough to become, at least in principle, a place where something might be living. But we are not here tonight to follow that thread. Not fully. Not yet. Because it leads somewhere else entirely. Somewhere much more complicated and much less restful than where we are going. What matters for methone is not what is in the ocean beneath Enceladus. What matters is what comes out of the tiger stripes. The exhalation. The breath of ice. Those plumes, rising from the South Pole, produce particles so small they are almost impossible to imagine. submicron to a few microns across, which means smaller than a wavelength of visible light, smaller than a single bacterium, smaller than the smallest grain of talcum powder you might touch between your fingers. These are not particles in any ordinary tactile sense. They are practically vapor made solid, dust at the frontier of what dust can be, ice that is more like an idea of ice than ice, as you would encounter it on any surface you have ever walked on. And in enormous numbers, continuously generated, continuously replenished, they rise from Enceladus and drift outward into the space around Saturn, settling into the broad, hazy, diffuse structure of the E-ring. The E-ring is not like the famous rings of Saturn that you can see in a photograph, the sharp, bright, geometrically perfect rings of the main ring system, made of larger ice chunks, catching the sunlight and throwing it back in that luminous arc. The E-ring is different. It is broad and dim and spread out, occupying an enormous swath of space between roughly 3 and 8 Saturn radii from the planet's center. You would not see it easily from Earth, even with a good telescope. It is more absence than presence, more the memory of a boundary than a hard edge. But it is full of those sub-micron grains of Enceladus ice, billions upon billions of them, drifting slowly, settling where they settle, coating what they coat, and right in the middle of the densest part of that ring, right where the concentration of those particles is highest, where the dusting is most persistent, where an object placed here would accumulate the finest, most continuous coating imaginable, is a band of space orbiting between the larger moons, Mimas and Enceladus. And in that band, 3 small moons are drifting, Methone, Anthe, Pallene. They are called, collectively, the Alkyonides, the name given to all 3 as a group, as if the astronomers who named them felt the kinship between them deserved to be acknowledged in the title, felt that 3 small things drifting together in the same band of space, embedded in the same ring, shaped by the same forces, deserved a single name that recognized what they share. The Alkyonides are the 7 daughters of the giant Alcyoneus in Greek mythology, and in the mythology they are remembered for their grief. When their father died, they mourned so deeply that the gods, moved by something, transformed them into birds that live on the sea. In astronomy, 3 of those daughters became 3 small moons of Saturn, orbiting quietly in the E-ring's deepest zone, coated in the same ice, shaped by the same gentle forces, smoothed by the same endless dusting. Methone is the largest and the best resolved, the one Cassini managed to fly close to on that single afternoon in May 2012. Anthe and Pallene are similarly small and, from what the images show, similarly smooth in appearance, though neither has been resolved to the same clarity as Methone, and neither produced the same quiet shock that Methone's images produced when the scientists first processed them and found a surface with nothing on it, no craters, no gouges, no record of anything that had ever struck it. The Alkyonides share a neighborhood, share a coating source, share the same strange fate of being buried in the finest ring material Saturn produces. They are, in a sense, all doing the same thing, all being dusted, all being smoothed, all being erased, but Methone is the one we have seen clearly, the one that showed us what that process looks like when it is running on a surface that has been giving into it for long enough. And Methone's position in the ring matters enormously. This is not incidental. The Alkyonides orbit inside the densest part of the E-ring, which is exactly where the concentration of Enceladus grains is highest, which means these 3 small moons are not merely passing through the ring's outer edges and picking up a little dust, they are embedded in the most heavily laden part of the ring. orbiting through the thickest distribution of those submicron ice grains that Enceladus continuously produces. If you imagine the E-ring as a broad, diffuse snowfall spread across a huge area of space, then the Alkyonides are not standing at the edge of the snowstorm, catching a few flakes on their outer surfaces. They are standing at the center of it, where it is snowing hardest, where the flakes come down most thickly and most constantly, where the accumulation is most persistent and most complete. This is why Methone looks the way it looks. Not because it was lucky, not because it was born smooth, not because nothing has hit it, but because it orbits in the one part of the Saturn system where the softest, finest, most mobile coating material in the solar system falls most densely, and because the physical properties of methone itself, its low density, its loosely bound interior, its near-nothing gravity, make it the perfect recipient. The supply is abundant. The acceptance is total. The result is a surface that has no craters visible in any image we have ever taken of it. That surface is bright. This is something the Cassini images confirmed, and that matters as a piece of evidence in its own right. Methone's surface has a high albedo, meaning it reflects a large fraction of the sunlight that strikes it, more than you would expect from an old, weathered, uncoated surface that had been sitting in space for billions of years, accumulating radiation damage and micrometeorite darkening, the way most surfaces in the outer solar system gradually do. Old surfaces tend to darken. They accumulate the slow chemical damage of space exposure, the subtle reddening and browning of irradiated organics and silicates, the patina of age that shows up in the data as a lower reflectivity. Methone does not have that. Its surface is bright and clean, consistent with a fresh coating of unweathered ice grains that have only recently arrived, grains that have not yet had time to accumulate the damage that would dim them. This is the albedo signature of resurfacing, of a coating that is not just present but continuously renewed, a surface that in some physical sense is always young because it is always being replaced by something new falling from the ring. The brightness of methone is in this way a record of a process, even though the surface itself keeps no records. It is the color of something that is constantly beginning again. And the resurfacing is external. This is important and worth sitting with for a moment, because external resurfacing is a different kind of thing from what happens on a geologically active world. On Enceladus itself, the surface is being remade from the inside out. Heat from the interior drives the plumes, keeps the subsurface ocean liquid, fractures the crust along those tiger stripe lines, and sends fresh material outward through internal pressure. The smoothness on Enceladus, where it exists, is connected to internal geological forces, to something happening inside the moon that expresses itself at the surface. Methone is not like that. There is no evidence in any Cassini data that methone has any active internal geology at all. No heat signature suggesting a warm interior, no fractures suggesting internal pressure finding a surface escape. No plumes, no geysers, nothing moving from the inside outward. What happens to methone happens from the outside inward. The material arrives. It settles. It accumulates. The surface accepts it passively, the way a field accepts snow, not generating it, not producing it, simply receiving what falls and holding what it can. The smoothness is not the signature of methone's own geological activity. It is the signature of Methone's position, its orbit, its address in the ring, its luck of being exactly where the snow falls thickest, and its physical constitution being perfectly suited to hold that snow in a loose, continuous, mobile blanket that fills every irregularity and softens every edge. There is something almost meditative in this distinction. A world that does nothing dramatic to itself, that does not erupt or fracture or flow from within, but that keeps its face smooth simply by being in the right place and remaining open to what arrives. Methone is not doing anything to achieve its smoothness. It is simply there, where the ring is, in the cold and the silence, and the ring does the rest. Methone also has its own contribution to the ring, in a small way, as if the relationship is not entirely one-directional. In 2006, Cassini detected a faint partial ring arc associated with methone, a short curved band of material sharing its orbit, a thin smear of particles tracing the same path through space that methone traces. A ring arc rather than a complete ring, because the material has not spread evenly all the way around. Anthe and Pauline have comparable structures. These arcs are not grand features. They are not the kind of thing that makes a dramatic photograph. They are more like whispers than statements, barely there, detectable only through careful analysis of Cassini's data. Present, not as anything you would see with your eye, but as a subtle statistical signal in the distribution of particles along the orbital path. What produces these arcs is not entirely settled, but the leading understanding involves the same resonance dynamics that shepherd methone into its wobbling orbit. The gravitational influence of mimas confining particles to particular zones along the orbital path and preventing them from spreading uniformly all the way around. The ring arc is, in a way, the material equivalent of the libration wobble. Both are the signature of Mimas's gravitational hand, organizing, confining, shaping the behavior of what orbits in this region of space. Mimas is not a background character in the story of Methone. It is a constant, subtle gravitational presence, pulling the tiny moon back and forth along its orbit, shaping the distribution of material around it, bending the very dynamics of the neighborhood in ways that leave their mark even on a surface with no marks on it. The ring arc detected in 2006 implies that methone is not just a passive recipient of ring material, but also, in small ways, a source, that particles escape from its surface or are liberated by small impacts and enter the ring system at the orbital distance of methone's own path. The relationship between methone and the E-ring is, in this way, something more like a circulation than a simple one-way flow. Material arrives from the ring, some of it is absorbed into the surface mantle, some of it may be re-released by impacts or by the extremely low gravity failing to hold the finest, loosest grains. And what is released joins the ring arc, where it orbits for a while before eventually spreading further or falling back. Methone is both a destination and, in a very small way, a contributor. It participates in the ring rather than simply receiving it. There is an analogy that helps make sense of the physical process happening inside methone's surface, helps explain how a layer of powder, however fine and deep, can erase an impact crater the way water erases a footprint in wet sand. The analogy comes from somewhere much closer to home than the outer solar system. In recent years, the NASA OSIRIS-RX mission visited an asteroid called Bennu, and the Japanese Hayabusa 2 mission visited a different asteroid called Ryugu. And both missions found something unexpected at the surface of these objects. Something that changed how planetary scientists understand what happens to small, loosely bound bodies when things hit them. Bennu and Ryugu are rubble pile asteroids. They are not solid rocks. They are collections of rubble, loosely bound together by their own weak gravity, structured more like loosely piled gravel than like solid stone. And what the missions found when they studied the surfaces closely was that when something small hits a rubble pile asteroid, even something too small to leave a visible crater on a solid rocky body, the impact sends vibrations through the whole loosely packed structure, and those vibrations cause the regolith, the loose surface material, to behave in ways that are more like a fluid than like solid ground. Particles shift, material slumps. Features that existed before the impact are smoothed or erased or reoriented. On a rubble pile in low gravity, an impact does not just leave a hole, it rearranges things. It causes the surface to flow, briefly, in response to the shock, and when the flowing stops, the surface is slightly smoother, slightly more settled, slightly more equilibrium-seeking than it was before. Scientists call this process impact gardening. Methone is impact gardening at its most extreme. The mechanism is the same. Impacts cause the loose material to rearrange, to flow, to settle, but on Methone, the conditions push the process to a result that Bennu and Ryugu never quite achieve. The surface gravity is so close to nothing. The particles making up the mantle are so extraordinarily fine. The material is not silicate regolith, but ice grains at submicron scale, so small and so loosely bound to each other and to the surface that even the most gentle disturbance would send them flowing. On Bennu, you can still see large boulders and some irregular topography because the material, though loose, has enough mass and enough mutual cohesion to maintain some structure. On Methone, the material is finer than Bennu's by orders of magnitude. The gravity is weaker by another large factor, and the supply from the E-ring continuously refreshes the finest topmost layer with new particles that have not compacted, have not fused, have not gained any cohesion at all. The result is a surface that cannot hold a crater. Not because the impactor does not arrive, it does. Things collide with Methone. The region of space Methone occupies is not empty. There are micrometeorites, dust grains, particles drifting through the E-ring at their own velocities and their own trajectories, and some of them strike Methone. The question was never whether impacts happen. The question was why they leave no trace. And the answer that Thomas et al. Worked through from the triaxial shape data and the density estimate and the physical properties of the E-ring material is that the trace is erased almost immediately. The surface flows, the mantle relaxes. The fine particles, barely bound, barely coherent, move in response to the disturbance, the way the surface of very still water moves in response to a drop falling into it, with a ripple, with a small rearrangement, and then settling back to smooth, because smooth is what low energy and gravity and fine particle size produce when given enough time to settle, and on Methone there has been time, there has been an enormous amount of time, and the settling is what you see in those images. Ryugu and Bennu gave us a model for what loosely bound surface material does when hit. Methone took that model and extended it to the point where it erases itself completely. There is something in this that is easy to carry alongside you into sleep, if you let it. The image of a surface that is struck and does not remember. A surface where the arriving thing, however hard it travelled, however long the journey from some distant orbit, sinks into the powder, and the powder closes around it, and by the time the settling is done there is nothing visible, nothing left in the surface record to say that anything arrived at all. The impactor is absorbed. The scar is filled. The surface breathes out, slowly, the way a very deep sleeper breathes, and returns to what it was before, unmarked, seamless, holding nothing of what just happened to it. Billions of years of this. The powder arriving, the impacts landing, the surface flowing and settling and filling. And still the same smooth egg, the same pristine face, the same surface with no age and no record and no scar. Methone is not being protected, it is not hiding, it is not particularly lucky, it is simply made of something so soft and so fine and so loosely held, and it orbits in a place where the softest possible coating material arrives most abundantly, that it has become incapable of holding a mark. And that incapability, that complete, total, physical inability to remember a scar, is what makes it one of the smoothest, solid surfaces ever imaged in the entire solar system. Not smooth because nothing happened, smooth because nothing could leave a trace of what happened. Smooth the way a long and restful night makes smooth the face of someone who went to bed carrying the full weight of something difficult, and woke in the morning without the crease of it visible anywhere. The E-ring falls on it still. Enceladus breathes still. In the cold, at 190 degrees below zero on the Celsius scale, so cold that the ice grains never compact, never fuse, never lose the lightness and the mobility that make them the perfect material for filling and smoothing, at that temperature, the behavior of the particles is the behavior of very dry, very fine dust, rather than anything that could be called snow, in the sense you might experience it on a cold morning at home. There is no stickiness in particles this cold, this small, this isolated from each other. They pile loosely, they rest lightly, they shift at the smallest provocation and settle back as flat as physics allows them to settle. And methone, embedded in the densest part of this invisible snowfall, turning slowly in its tidally locked orientation, with its long axis pointed toward Saturn, keeps accumulating, keeps settling, keeps smoothing out. Anthe and Pallene orbit nearby, smaller and less well observed, but almost certainly doing the same thing in the same way. The three Alcyonide daughters of mythology transformed into three small powder-coated eggs of moons drifting in a river of ice between the two larger moons that bracket their neighborhood, Mimas on one side and Enceladus on the other, the resonance shepherd and the breath source, the gravitational boundary and the snowfall engine, and between them the three small, smooth worlds, absorbing what arrives and holding no record of any of it. The ring connects them all. The ring is the medium through which Enceladus's extraordinary interior heat reaches Methone's extraordinary exterior surface, the invisible infrastructure of the Saturn system that turns the subsurface ocean of one moon into the polishing coat of another. It is a connection that would be almost impossible to intuit from any single observation. If you had only the Cassini images of Methone, the smooth, featureless egg, the remarkable absence of craters, you might wonder about internal geology, about some process at work beneath that surface. And if you had only the Cassini data from Enceladus, the tiger stripes, the plumes, the evidence of a warm ocean, you might not immediately think of a tiny smooth moon orbiting nearby. The connection emerges only when you hold both things at once and then look at the ring between them, the ring that carries material from one to the other in those sub-micron particles that are both too small to see individually and collectively responsible for one of the most striking surfaces in the solar system. It is, in the end, a kind of gift. An unintended one. Enceladus is not trying to polish Methone. There is no intention in any of this, no directed process, only the mechanics of orbits and gravity and the physics of particles under very cold conditions at very low pressures in the presence of a very large planet and its complicated ring system. And yet the result, seen from the outside, has the quality of something deliberately achieved. A surface so perfectly maintained, so continuously refreshed, so utterly without blemish or scar, that it seems almost to be cared for. It is not cared for. It simply is what it is, in the place that it is, receiving what arrives and holding the shape that physics requires it to hold. But the image is hard to resist. In the quiet of this long descent into the details of a world you will never visit, a world that the only spacecraft capable of visiting has already visited and left and ended its mission in the atmosphere of Saturn and is gone. The image of a small, smooth moon in the cold and the dark, being endlessly, quietly, unhurriedly coated in the finest ice that any ocean anywhere in the solar system has yet exhaled into space. The chain is complete, the source is understood, the powder arrives, settles, smooths, and the surface holds its shape and its silence and its absolute, unbroken record of nothing at all. And yet to understand just how extraordinary that record of nothing is, it helps to look in the other direction. Not inward, toward the mechanism that produces the smoothness, but outward, toward the neighbours, the worlds that share Methone's part of the Saturn system, that orbit in the same cold dark, that receive the same particles drifting outward from Enceladus, and that have nevertheless ended up looking nothing like it at all. The most dramatic of those neighbours is Mimas. Mimas is not a small moon. It is, in fact, the smallest of Saturn's moons that has been pulled by its own gravity into a roughly spherical shape, a threshold that takes considerable mass to cross, a shape that requires the interior to be heavy and cohesive enough to collapse inward on itself under its own weight until it rounds out. And it sits close enough to Methone that they are, in any meaningful sense of the word, in the same neighbourhood of Saturn's system. They are not distant relatives. They are next-door neighbours, sharing a broad stretch of the same orbital space, both embedded in the same diffuse ring material, both subject to the same rain of particles drifting outward from the plumes of Enceladus, both swept by the same slow, invisible current of micron-sized ice that flows through this part of the system like a breath that never quite stops. And Mimas looks like it has been through a war. The crater that defines Mimas, the one that has given it its famous resemblance to a certain fictional space station in a certain science fiction film franchise, is called Herschel, named for the astronomer William Herschel, who discovered Mimas itself in 1789. Herschel crater is enormous. It spans roughly 1/3 of Mimas's entire diameter. If you were to take the moon and lay the crater across it, it would cover nearly a continent's worth of surface on a world that has continents only in the loosest, most generous use of that term. The walls of Herschel rise about 5 kilometers from the crater floor. The central peak, the rebound mountain that punched upward from the crust after the impacting body hit, rises another 6 kilometers. Whatever struck Mimas to leave that mark hit so hard that the shockwaves from the impact are thought to have passed entirely through the body and cracked the surface on the far side. Mimas survived it. Barely, scientists believe, in the sense that an impact only slightly more energetic would have shattered the moon entirely, rather than merely carving a basin 1/3 of its diameter wide. But it survived, and it carries that scar with it everywhere it goes, around and around Saturn, the great hollow eye of Herschel, always there, always permanent. always recording in the crust of the moon the fact that something enormous hit it at some point in the deep past, and that the record of that event has nowhere to go and nothing to erase it. This is what most of the solar system looks like. This is the default condition of a rocky or icy body moving through space over billions of years, accumulated marks, accumulated history, accumulated evidence of every large impactor that came close enough and fast enough to leave a dent. The surface of a world, in the ordinary course of things, is a kind of archive, not an organized one, not a legible one in any human sense, but an archive nonetheless, written in the language of craters and fractures and ejector blankets and secondary craters from the material thrown outward by the primary impact. Read a cratered surface carefully enough, and you can, at least in principle, reconstruct something of a moon's history, which parts are older, which parts were resurfaced by later events, which directions the ancient impacts came from, how the flux of impactors has changed over time. Mimas is readable. Its surface, however brutal and battered it looks, is a document. Methone, 3 kilometers wide and drifting in the same part of the system, has nothing written on it at all. The contrast between them, vast scarred Mimas with its Death Star crater, and tiny, seamless Methone with its unbroken egg-shaped face, is one of the more quietly astonishing things in the Saturn system, and it sits in the same slice of orbital space, close enough that if you were somehow floating at a fixed point between them, you could, with the right eyes, see them both at once. One a record of everything the solar system ever threw at it, the other a surface that cannot be made to remember anything. And the connection between them runs deeper than proximity. Because Mimas and Methone are not simply near each other, they are gravitationally entangled in a specific, measured, ongoing relationship that has consequences for both of them. The larger moon and the smaller one are locked in what astronomers call a mean motion resonance, a condition in which the orbital periods of two bodies form a simple ratio and each body feels the gravitational nudges of the other arriving in a regular rhythm, like a push on a swing, timed to always arrive at the same point. The resonance between Mimas and Methone is a 14-15 relationship. For every 15 complete orbits Methone makes around Saturn, Mimas makes almost exactly 14. The numbers are close enough that the gravitational tugs accumulate rather than cancelling, pulling Methone's orbit into a specific pattern and holding it there. The most visible consequence of this is that Methone does not travel around Saturn in a perfectly steady path. Its longitude, its position along its orbital track, wobbles, liberties, astronomers say, using the technical word for an oscillation around a fixed point, the same word used for the slight rocking of the moon as seen from Earth that allows us to see just over the edge of the lunar limb. Methone's libration is not a visual rocking, but a gravitational one, a back-and-forth wandering of the moon's position along its orbit by several degrees, which translates to something on the order of tens of kilometers in either direction. Methone is, in a sense, swaying slightly in place, rocking gently in the orbital groove that Mimas has carved for it through the steady accumulation of gravitational nudges delivered 14 times for every 15 loops it makes around the planet. There is something almost companionable in this, in the image of a large battered moon maintaining a gravitational conversation with a tiny smooth one, each one going around Saturn in its own path, each one feeling the presence of the other in the regular rhythm of those nudges. Mimas does not know Methone is there, in any meaningful sense. There is no knowing in any of this, but the mathematics of their interaction is precise and ongoing, and it has been ongoing for as long as both moons have occupied their current orbits, which is itself a span of time almost impossible to hold in the mind without letting go of most of what you know about years and lifetimes and human duration. It is worth pausing in the middle of this long, quiet descent into the particulars of a world 3 kilometers wide to consider what else Saturn has done with the same raw material, the same ring particles, the same orbital zones, the same available supply of fine icy dust, when it had a different set of conditions to work with. Because Methone is not the only small moon embedded in Saturn's ring system, and not all of them ended up smooth. Pan is one of the most distinctive small moons in the solar system, and it does not look anything like Methone. Pan lives inside the Encke Gap, a clear lane in Saturn's A ring that it has carved out through its own gravity, sweeping the gap clean with each pass the way a broom clears a path through dust. What makes Pan remarkable is its shape. It has a sharp equatorial ridge, a raised belt of material running around its middle, as if someone had carefully pressed a ring of dough onto the surface of an already roughly spherical object and left it there. The result is a shape that scientists, with a mix of precision and affection, have compared to a ravioli, or to a flying saucer, or to a walnut with a pronounced seam. The ridge is thought to have formed when ring material was drawn in by Pan's gravity and settled preferentially onto the equator, piling up there because the geometry of the orbit and the angles of approach funneled material to that latitude and no other. Atlas has a similar feature. So does Daphnis, another small moon living inside another ring gap. These are moons that have also been accumulating ring material, also collecting the particles that drift through their orbital neighborhoods, also building up coatings of material gathered from the ring environment. But the outcome in each case is different. Not a uniform blanket, not a smooth all-over coating, but an equatorial pile. A specific geometric deposit shaped by the orbital mechanics of a body embedded in a thin ring structure that feeds material in from specific directions and specific angles. The difference between what happened to Pan and Atlas and Daphnis and what happened to Methone comes down to position, density, and the character of the material being accreted. Pan and its ravioli-shaped cousins orbit in the dense, narrow A-ring, where the material arriving is concentrated in a thin plane and arrives predominantly from the equatorial direction. Methone orbits in the broad, diffuse E-ring, where the material is dispersed throughout a vast volume and arrives from many angles, wrapping the moon in a more even and uniform way. Pan accretes a ridge. Methone accretes a blanket. Same process, different geometry, different result, which is to say that the solar system does not have one trick for small moons in ring systems. It has several, and the outcome of each depends on the specifics of the environment in ways that are only beginning to be fully traced. Methone's outcome: the blanket, the smooth uniform coating. The total erasure of surface texture is the rarest of the variants, or at least the rarest that has been imaged well enough to see clearly, and it sits within a much larger collection. Saturn, as of 2025, has 274 confirmed moons. 274. The count continues to grow as survey telescopes sweep the outer reaches of the Saturnian system and detect smaller and smaller bodies, most of them irregular, most of them dark, most of them too distant and too faint and too small to be seen in any detail. The number is large enough to feel slightly unreal, the kind of number that the human mind accepts as data before it quite absorbs it as a quantity. 274 objects, ranging in scale from Titan, a moon larger than the planet Mercury, with a thick nitrogen atmosphere and lakes of liquid methane on its surface, down to captured irregular bodies barely a kilometre wide, tumbling in remote inclined orbits far from the planet. Ancient debris that Saturn's gravity caught at some point in the early solar system and has never let go. Among all of them, Methone stands as one of the smoothest solid surfaces that has ever been imaged, not the largest, not the most massive, not the most volcanically active, or the most geologically complex, or the most likely to be discussed in the context of life, but, in its specific quality of surface smoothness, among the most striking. One world, 3 kilometers across, in a system of 274, and the thing that marks it out from all the rest is the thing that is not there. No craters, no texture, no record. The absence is the feature. And what makes the absence particularly strange, in the way that scientific strangeness works, the kind that sits quietly and becomes stranger the longer you look at it, is what it implies about time. On a cratered world, the craters are time. They are the physical embodiment of elapsed duration, of the slow accumulation of events across millions and billions of years. Count the craters, and under the right conditions you can estimate the age of the surface, at least in relative terms. A region with more craters is older than one with fewer, because older surfaces have had longer to collect impacts. The crater record is a clock. Methone has no clock. Or rather, it has a clock, but the hands are always being reset to 0. Every impact that would mark a moment in time on Methone's surface is swallowed back into the loose powder of the mantle, filled in and covered over and smoothed out until there is nothing left to date. Nothing left to count, nothing left to read. The surface of Methone is eternally young, in the most literal sense possible, not young because it formed recently, but young because it is continuously renewed, continuously resurfaced, continuously returned to the same blank beginning, regardless of what has happened to it. It presents an unmarked face to every instrument that looks at it. Not because it has not been struck, but because it cannot be made to show the evidence of being struck. This is what the powder does. This is what the E-ring's endless supply of submicron ice grains, exhaled from Enceladus and carried through the darkness to settle on Methone, has accomplished over however long the system has been in its current configuration. It has given Methone a surface that has no past, or rather, a surface from which the past has been continuously, gently, unhurriedly removed. There is a particular quality to the idea of a world with no visible age. It is neither a comforting nor an uncomfortable thought at first. It simply sits there, slightly outside the reach of the usual frameworks. We are accustomed to age showing. We are accustomed to the idea that time leaves marks, that the longer something has existed, the more evidence it carries of its existence, that surfaces accumulate history the way fabric accumulates wear. A new thing looks new, an old thing looks old. Even in geology, even on the slow timescales of planetary surfaces, the principle holds: the older the terrain, the more it has been battered, the more craters it has collected, the more worn it looks. Methone inverts this. It is not a new thing. It formed in the early solar system, in whatever process assembled the moons and moonlets and ring particles of the Saturnian system, and it has been in its current orbit for what is very likely a very long time. But it does not look like an old thing. It looks like something that has never been touched. something that arrived exactly as it is, smooth and egg-shaped and featureless, and has always been this way, and will always be this way, as long as Enceladus continues to feed the E-ring, and the E-ring continues to drift outward and settle on Methone's surface, and the surface continues to flow and relax and absorb whatever marks it accumulates. We will never know what its oldest craters look like. They are gone. Long gone, almost certainly, erased not all at once, but one by one, each one slowly filled and smoothed and incorporated back into the general surface, the way a footprint in very fine dry sand fills itself in over a few hours, until there is no longer any trace that a foot ever rested there. Methone is that sand, at a planetary scale, in slow motion, over geological time. The discovery of all this, of the smooth surface, the egg shape, the near-zero density, the mantle of fine particles, the whole extraordinary condition, happened on 1st June 2004, when the Cassini Imaging Science Team, examining images returned by the Cassini spacecraft on its way through the Saturn system, found a small, faint object in an orbit between Mimas and Enceladus that had not been there in the catalogue before. A point of light, an unresolved point, too small and too distant to show any detail, just a signal against the dark, a brightness that moved in a way consistent with a satellite, and was accordingly catalogued and given the provisional designation S/2004 S1. One of what would become a series of new moons discovered by the Cassini mission, each one a point of light at first, and a world only later if the spacecraft ever swung close enough to look. Methone was eventually given its name, Methone, by the International Astronomical Union, and the name came from mythology, as it does for so many of the objects in the outer solar system. Methone was one of the Alkyonides, the 7 daughters of the giant Alkyonius in Greek tradition. The Alkyonides were figures of sorrow in the old stories. They mourned their father after he was killed by Heracles, and their grief was so great that the gods transformed them into birds, into the kingfisher birds called alcyons, which gave their name eventually to the English word halcyon. The halcyon days, the days of calm, the period of still and peaceful weather that legend said the kingfisher needed to nest safely on the surface of the sea, that Aeolus, the god of winds, held in check each winter for 14 days so that the bird could raise its young in peace. Methone, named for a daughter of sorrow who became a bird of calm. And orbiting Saturn in a cluster with her sisters, Anthe and Pallene. The other 2 Alkyonides moons, the other 2 small faint bodies sharing the same orbital zone between Mimas and Enceladus, each one similarly smooth, similarly tiny, similarly coated in the gentle rain of particles from Enceladus. The 3 of them together in their cluster, like 3 halcyon birds resting on the surface of a quiet sea, in the days when the winds are held still. The name was not assigned with any of that in mind, of course. Names come from committees and conventions and the need for a consistent naming scheme that associates the moons of Saturn with the right traditions. But the fit is there, in the way that sometimes a name and a thing align without any intention behind the alignment, and once you see it, you cannot quite unsee it. 3 small smooth moons in the halcyon zone between 2 giants, being endlessly, quietly covered in a substance finer than anything the human hand can feel, kept smooth and still and unmarked by a process that requires nothing more than gravity and cold and the slow drift of particles through the dark. The spacecraft that found them, and that eventually came close enough to show us what Methone actually was. had been travelling for a long time before it arrived. Cassini launched on 15 October 1997 from Cape Canaveral on a Titan I rocket with a Centaur upper stage, carrying instruments from 17 countries, the product of decades of planning and engineering and political negotiation between space agencies on opposite sides of the Atlantic. It travelled for nearly 7 years before it arrived at Saturn, swinging past Venus twice and Earth once and Jupiter once to gather the gravitational momentum it needed, and it arrived at Saturn on 1 July 2004, slowing into orbit in a maneuver that required its engine to fire for 96 minutes in the precise right direction at the precise right moment, with no possibility of human intervention because the signal delay between Saturn and Earth made real. Time commands impossible. It worked. The engine fired and stopped, and Cassini was in orbit around Saturn, and it would remain in orbit for 13 years, sweeping through the system in hundreds of different orbits, past Titan and Enceladus and Mimas and Iapetus and Phoebe and dozens of others, collecting data of every kind: images, radar maps, magnetometer readings, mass spectrometer analyses, radio science profiles, dust counts. It discovered the plumes of Enceladus. It mapped the tiger stripes. It found the subsurface ocean. It discovered new moons, including the faint dot that became Methone, and it eventually, on 20 May 2012, swung close enough to that dot to resolve it into a world. 1,900 kilometers. That was the distance at closest approach, close enough to see that the surface was smooth, that it was egg-shaped, that it had no visible craters at the resolution available, that it was something that had no clear precedent among the small inner moons of the solar system. The images came back. The science team looked at them. Thomas and colleagues analyzed the shape and the density implications and published their findings in Planetary and Space Science in 2013. And Methone was, for the first time, understood, and then Cassini moved on. Because a spacecraft in orbit around a planet does not stay at any one point, it keeps moving, keeps following the orbital path it is on, keeps falling forward around Saturn in the long ellipse of whatever trajectory the mission plan requires. The flyby of Methone was one event among many, one data point in a 13-year accumulation of observations, and the spacecraft moved on, and Methone was left behind in its orbit with its smooth face and its powder mantle and its eternal blankness. On 15 September 2017, after 13 years in the Saturnian system, Cassini ran out of fuel. The mission controllers, knowing the end was coming, and knowing that the spacecraft's fuel was nearly exhausted, and knowing that there was no way to maintain controlled flight indefinitely, made a deliberate decision. They would not leave Cassini in orbit to drift and eventually impact one of Saturn's moons, uncontrolled, risking contamination of a world that might, possibly, harbour some form of life. Instead, they would fly the spacecraft directly into Saturn's atmosphere, a final plunge, a controlled destruction, a death by incineration in the clouds of the planet it had spent 13 years studying. They called it the grand finale. On the morning of 15 September 2017, Cassini made its final transmission and entered Saturn's upper atmosphere and was destroyed. The signal reached Earth at about 7:55 in the morning, Eastern Time, and the team at the Jet Propulsion Laboratory in California received it and watched their tracking screens go still and knew that the spacecraft was gone. Some of them wept. It is a strange kind of grief to mourn a machine, but the machine had returned more than 300,000 images and more data than anyone had fully processed, even years later, and it had shown humanity things about the Saturn system that could not have been imagined before it arrived, and now it was gone. incorporated into the planet it had circled for so long. And there is no current spacecraft at Saturn, and there is no confirmed mission scheduled to return, and the images of Methone taken on 20 May 2012 are, for the foreseeable future, the only close images of Methone that exist. One flyby. 13 years of orbital mechanics to arrange it. A moment of passage, and a few images returned across the darkness. And then nothing more, only the continuing silence of the moon itself, and the continuing patience of the powder, and the continuing blankness of the surface that has nothing to remember and everything to smooth away. This is the condition that Methone sits in now, as it has sat since before the Cassini mission, and as it will sit long after any human generation alive today is gone. It goes around Saturn once every 1.01 Earth days, just over 24 hours, just over the length of a day on the world where you are lying right now. In the time it took you to get from the morning to this late hour, Methone made nearly one complete circuit of an enormous planet 1 billion miles away, shedding any mark it might have received along the way, settling back into its smooth shape. Its tidally aligned long axis pointing toward Saturn the way a compass needle points toward north, its surface holding the quiet equilibrium that its physics requires and its environment maintains. And this is the thing that the whole long descent into these details has been building toward, not a mystery in the dark, not a puzzle without a solution, but something rarer than a mystery, an explanation that is as beautiful as the thing it explains. Methone is smooth because it cannot hold a scar. It cannot hold a scar because it is barely solid, a loosely bound aggregate of fine particles. Porous as a snowbank, with a density roughly a third of water ice and a gravity so faint that the surface grains are barely bound at all. It cannot hold a scar because the mantle of powder that blankets it flows as slowly and as completely as a fluid, filling any impression, relaxing any disturbance, returning always to the equilibrium shape that physics requires. And it has an endless supply of new powder to do this with. Because a moon on the other side of the gap, Enceladus, with its tiger-stripe fractures and its hidden ocean and its towering plumes of vapor and ice crystals erupting into the dark, is continuously, patiently, without any directed intention, exhaling the finest snow in the solar system into the ring that carries it outward and settles it down onto Methone's surface like a covering, like a blanket, like the slow accumulation of something gentle falling through the dark. Every blow absorbed, every mark erased, every scar forgotten by the time the next orbit begins. There is a quality to that image, not mystical, not metaphorical in any way, that exceeds what the physics actually requires, but nonetheless resonant in a way that seems worth pausing inside for a moment before the night closes over it, the image of a surface that holds no record of what has struck it. That keeps no account of damage. That does not carry forward the evidence of every difficult thing that arrived and made contact and tried to leave its mark. The mechanism is cold and physical and has nothing to do with intention or mercy or any of the human concepts that the image might seem to brush against. It is simply the result of very fine powder in very low gravity at very cold temperatures in the presence of an enormous planet and its complicated ring system. That is all it is. And yet, to lie in the dark and consider a surface like that, a surface that accepts everything that comes at it and releases the evidence of all of it, that presents the same smooth, unmarked face each morning, regardless of what the previous day contained, that has the capacity not for peace exactly, but for something that peace is built from, which is the simple inability to hold on to damage, is to feel something quiet settle, not an instruction, not a lesson in any prescriptive sense, just a fact, held lightly in the mind the way you hold a smooth stone, feeling the temperature of it change slowly toward your own, feeling the particular stillness of a thing that has no edges you can catch your thoughts on. Methone is like that. 3 kilometers wide, smaller than the distance you might drive to a grocery store, floating in the cold 1 billion miles from where you are, attended by the silent company of the E-ring and the distant noise of Enceladus's geysers and the gravitational conversation with Mimas that rocks it gently back and forth along its orbit. It has been there longer than the word ancient has any real meaning for. It will be there long after any of this, any of the words in this narration, any of the missions that have studied it. Any of the people who looked at the 2012 images and tried to understand what they were seeing is gone. And its surface will still be smooth, still unmarked, still receiving and still releasing, and still holding the shape that physics requires it to hold. Methone, daughter of Alcyonius, sister of Anthe and Pallene, one of the Alcyonides, the halcyon moons in the quiet zone between two giants. The moon that forgets, the moon that cannot be made to remember. If you have stayed with this until now, through the E-ring and the tiger stripes and the powder finer than talcum and the Death Star crater on Mimas and the long, careful arc of the Cassini mission and the 7:55 moment when the signal stopped, then you have come a very long way tonight, from wherever you are to a world 3 kilometers wide in the cold dark of the outer solar system. And back again. That is a long way to travel in the time between putting down the day and finding sleep, and I am glad you made the journey with me. If you feel moved to leave a word in the comments, to say where in the world you are listening from tonight, what corner of the earth you are in, what kind of dark is outside your window, I would genuinely like to know. The comments are there, and I read them. There is something I find quietly grounding about knowing the places from which people choose to think about small, smooth moons on the edge of sleep. There are more slow stories here, of the same careful kind, waiting for whenever you want them, other moons, other mysteries, other things that the solar system has built in the dark that turn out, on close examination, to be stranger and quieter and more extraordinary than anything you might have expected to find. But not tonight. Tonight is done. The powder is settling on Methone's surface right now, at this moment. Whether you are asleep or still drifting toward it, the fine ice crystals from Enceladus's ocean finding their way through the vacuum and coming to rest on that smooth and patient surface and being absorbed into it without a mark, without a memory, without any record that they arrived at all. You have held enough in your mind for one night. Put down whatever remains of the day. Let it go the way Methone lets things go, not through effort, not through force, but through the simple, quiet physics of a surface that does not need to hold on. Let the smooth dark be what it is. Let the distance between here and Saturn be exactly as large and as restful as it is. Good night from up here in orbit. I will keep watch while you drift.